Simplex algorithm minimization case. When the constraints are of greater than or equal to type, convert it to equation by subtracting the surplus variables. To avoid violation of non-negativity condition of surplus variable, we add artificial variable AI to get an initial basic feasible solution. Artificial variables have no meaning in physical sense and are only used as a tool for generating an initial LPP solution. Before the final simplex solution is reached, all artificial variables must be dropped from the solution mix, which is done by assigning appropriate coefficients to these variables in the objective functions. These variables are added to those constraints with equality and greater than or equal to sign. The artificial variables are removed using bigger method in which we assign coefficients to artificial variables. If the objective is to minimize, then a very large positive price or penalty is assigned to each artificial variables. Similarly, if it is to maximize, then a very large negative price or penalty is assigned to each artificial variables. At any iteration of the simplex algorithm, any one of the following cases may arise. If at least one artificial variable is present in the basis with a zero value and the coefficient of m in each Cj minus Sj value is non-negative, then the problem has no solution. Second one is if at least one artificial variable is present in the basis with a positive value and the coefficient of m in each Cj minus Sj value is non-negative, then there is no optimum basic feasible solution. Some complications in simplex problem. First one is unrestricted variables. In many practical situations, one or more variables can have either positive, negative or zero value. Such variables are unrestricted variables. To use simplex method, all unrestricted variables expressed as the difference of two non-negative variables. Second complication is type for entering basic variable. A situation may arise at the iteration when two or more columns may have exactly same Cj minus Sj value. In such a situation, we can choose the columns arbitrarily, or if the tie is between decision variable and slack variable, choose decision variables. The third complication is tie for leaving basic variable, which is known as degeneracy. If the minimum ratio is not unique or values of one or more basic variables in the xb column become 0, then the simplex iterations are repeated indefinitely without arriving at the optimal solution, which is known as degeneracy. Find solution using simplex method. Maximize is equal to 19x1 plus 7x2 subject to 7x1 plus 6x2 less than or equal to 42, 5x1 plus 9x2 less than or equal to 45, x1 minus x2 less than or equal to 4, and x1 x2 greater than or equal to 0. Here we can see that there are two variables x1 x2 and three constraints. Now the problem is converted to canonical form or standard form by adding slack, surplus or artificial variables appropriately. As the constraint 1 is of the type less than or equal to, we should add the slack variable s1. And the second constraint also of less than or equal to type, we should add second slack variable s2. And the third constraint also is less than or equal to type, add the third slack variable s3. After introducing slack variables, the problem becomes maximize is equal to 19x1 plus 7x2 plus 0s1 plus 0 into s2 plus 0 into s3 subject to 7x1 plus 6x2 plus s1 equal to 42, 5x1 plus 9x2 plus s2 equal to 45, x1 minus x2 plus s3 equal to 4, and x1, x2, s1, s2, s3 all greater than or equal to 0. This is known as the standard form of an LPP. Now we can form the initial simplex table or iteration 1. In this table, the first column corresponds to the basic variables. Here the basic variables are the slack variables s1, s2, s3. The second column corresponds to the coefficients of these basic variables in the objective function. They are 0, 0, 0, and the next column corresponds to the right hand side values in the equation, and next column x1, x2, s1, s2, s3. This corresponds to the values of the coefficients in the equation, and this Cj values are, they corresponds to the coefficients of x1, x2, s1, s2, s3 in the objective function. After that, we can calculate z value. Z equal to sigma cb into xb. So 0 into 42 plus 0 into 45 plus 0 into 4, so equal to 0. Then Zj corresponds to sigma Cb into Xj. That is first corresponding to the first column. Here 0 into 7 plus 0 into 5 plus 0 into 1. The value equal to 0. Similarly, we can calculate other values in that row. Then calculate Cj minus Zj. That is the net value. Then Cj, Zj values are here. We can calculate the corresponding values in that row. It is 19, 7, 0, 0, 0. After writing all the values in the table, see that the Cj minus Zj value, if the values are negative, then that corresponds that the solution is optimal. Here the values are not negative, so we have to see the living and entering variable. That is, look at the positive maximum of Cj minus Hj. Here it is 19 and the column index is 1. So that corresponds to the variable x1. So we can decide the entering variable is x1. Next we have to see which is the living variable. For that, use the minimum ratio. So to calculate the minimum ratio, calculate xb by x1. So here xb value is 42, x1 value equal to 7. So 42 by 7 equal to 6. Similarly, 45 by 5 equal to 9 and 4 by 1 equal to 4. Then of these values, which is minimum? Minimum value is 4. That corresponds to the row S3. So here the living variable will be S3. And look at the living row and entering column. The intersection is known as the pivot element. Here the pivot element is 1. Next we have to form the next table, that is iteration 2. To form the table, what we have to do is look at the pivot element. If the pivot element is 1, try to make other elements in that column 0. For that, we can use some elementary row operations. Here the pivot element containing in the third row, so keep that row itself. So new R3 equal to old R3, then new R1 will be equal to old R1 minus 7 times new R3, and new R2 equal to old R2 minus 5 times new R3. If you do these row operations, we can make the elements in the pivot column 0. Look at this table. The first column corresponds to the basic variable. So in that column S1, S2, instead of S3 leaves and X1 enters. And next column corresponds to the coefficient of basic variables in the objective function. So you write 0, 0, 19. Then next values in the table, we will get from this elementary row operations. So this will be the table. Next we can evaluate Z value as in the previous table. So Z equal to 76. Then calculate Zj values. Then calculate Cj minus Hj. So we can see that from this table, here there is a positive value. If all the values are negative, then we can see that solution is optimal. Here the positive value is there. So that column corresponds to x2. So the entering variable is x2. Now we have to find the leaving variable. For that, use the minimum ratio rule, that is calculate xb by x2. Then x2 must be greater than 0. Then calculate 14 by 13. Then 25 by 14. Here in the next x value, since it is negative, we cannot calculate that value. So look at these two values. Minimum is 14 by 13. So corresponding to that row is S1. So S1 will be the leading variable. Then the intersection of S1 and X2, S1 row and X2 column, the value is 13. It is known as the pivot element. From the previous table, we can see that the pivot element is 13. Next, to form the next table, you have to make that pivot element 1 and all other elements in that column 0. For that, we have to use the elementary row transformations. So the elementary row transformations are new R1 equal to old R1 divided by 13. Then new R2 equal to old R2 minus 14 into new R1, and new R3 equal to old R3 plus new R1. So the new table becomes, the basic variables are x2, s2, x1, and the corresponding values, coefficients in the objective function are 7, 0, 19. Then all other elements in that remaining columns we will get from the previous row operations. Then calculate Z, then see Zj values are here, then calculate the net value Cj minus Hj, and we can see that all the values are less than or equal to 0. That indicates that the solution is optimal. Since all Cj minus Hj less than or equal to 0, the optimal solution is arrived with the value of the variable as x1 equal to 66 by 13, x2 equal to 14 by 13, and maximum value is equal to 104.